Alright, so today we're going to continue talking about trig equations. Specifically, we're going to talk about trig equations where you have to use your calculator. So the best way of explaining this, I think, is to start with an example. So let's start with a really simple trig equation that requires your calculator. So consider the following equation. Sine of x is equal to 0.7. And let's suppose that I want my answers to be in radians. And I'm not putting any restriction on this equation, so I'm not demanding that x is be between 0 and 2 pi or anything. So there are going to be infinitely many solutions, and they should be in radians. So how do we do this? Well, the problem essentially is that 0.7 is not a unit circle value, right? If instead of 0.7 this were something more familiar like root 2 over 2, I would be able to list some base solutions. But because this is not a unit circle value, I can't do that, right? What I'm supposed to do is start by writing down base solutions and say, oh, I'm looking for angles whose sine is 0.7. One of them on the unit circle is this guy, and the other one is that guy. Those are my two base solutions, and I add 2 pi n to each one of them, and that's it. But I don't know any angles whose sine is 0.7, so what do I do? The answer is you use your calculator. So the first thing to understand is that one base solution, so first base solution, and as you know, we usually need two base solutions, right? But the first one is going to be given by your calculator. What you're going to do is you're going to use the inverse sine function, and you're going to apply it to 0.7. Okay. Now, before we compute what this is with my calculator, let's think about why this is actually a base solution. You know, what is a base solution anyway? Well, it's an angle, you know, on the unit circle whose sine is 0.7. It's really just a specific solution to this equation, right? And in other words, a base solution is really just an angle which satisfies this equation. It's an angle whose sine is 0.7. And that's exactly what this is. The inverse trig function produces an angle, and of course it's an angle whose sine is 0.7. So whatever this thing is, that's an angle whose sine is 0.7. That's going to be a base solution. So let's go ahead and compute it. For one thing, you really want to make sure you're in the right units here. I'm asking for solutions in radians, which means I need to make sure my calculator's in radians. How you do that depends on the calculator. For these guys with the TIs, you go to mode, this button here. And as you can see, I'm already in radians. If I were in degrees, this thing would be highlighted. So I'm in radians, so I'm going to ask for the inverse sine of 0.7. The inverse sine function is like the secondary button of the sine function, usually. So second sine, you can see the sine inverse, 0.7. Okay, 0.7753, blah, blah, blah. That's an angle, believe it or not, in radians. Okay, so that's my angle in radians. So this is about let's say 775. I want to keep at least 3 decimal places here, so I rounded to 3 decimal places. Okay, so that's one base solution. Cool. But as you know, we usually have 2 base solutions, right? And in fact, that's true here. We actually need 2 base solutions to generate all of the solutions to this equation. How do we get the other base solution? Your calculator can only give you the first one. To find the other one, you have to use your brain. Okay. Now let's think about this. I'm looking for 2 angles, right? 2 base solutions, that is, 2 angles whose sine is 0.7. I found one of them, 0.775 radians. You know, exactly where that is on the unit circle, like, I don't really know. Maybe it's like here. I have no idea what 0.775 radians looks like. I don't really know. But let's pretend that it's right here. Okay, so this angle right here is 0.775 radians. And what I'm looking for is the other angle on the circle which also has a sine of 0.7. That is, I'm looking for the other angle on the unit circle which satisfies this equation, the other base solution. Where is that going to be? Where's the other angle that has the same sine as the thing I've already found? Where's the other angle that has the same y coordinate as this angle right here? Well, it's going to be this one, right? It's going to be the one that you obtain if you, reflect across the y-axis. So whatever this angle is here, that's going to be my other base solution because this angle will also have a sine of 0.7 as desired. So what is that angle? More importantly, how do we find it? Well, you know, by symmetry, this little angle there is also 0.775. And so this angle that I'm looking at, this whole thing right here, is pi minus. So the second base solution. Second base solution, this angle right here, is actually going to be pi minus 0.775 radians, okay? That's going to give you this angle right here, right? Because pi is half a rotation. You subtract this guy, that leaves you with this, right? And that's actually true in every case that you're solving a sine function. Whenever you're solving a trigonometric equation and you have to use your calculator and you're using the sine function, the second base solution will in fact be pi minus the first base solution, okay? So you get your first base solution by using your calculator, taking the inverse sine of whatever number you have here. And then you get your second base solution by subtracting your first base solution from pi. So let's actually compute what this is. Pi minus 0.775. 0.775. I've got the answer right here. I might as well use more decimal places here. It's best not to round to the end if you can avoid it. Okay, so 2.366, rounded to 3 decimal places, that's 2.366. So, yeah, both of those angles are in radians. So this is one base solution, this is my second base solution, and just like always, all we have to do now is slap on a 2 pi n to each one of those, right? So x is equal to 0.775 plus 2 pi n, or x is equal to 2.366 plus 2 pi n. And that is, those two formulas represent the entire solution set to the equation. If I had some kind of a restriction, like if someone said, oh, I want 0 to be less than or equal to x, less than, you know, 5 pi or something, then you would have to start plugging in specific values of n, you know, and generating the actual solutions. But I don't have a restriction, so I just stop with these two formulas here. Okay. Let's do a second example, but this time let's do one involving a cosine function. As you'll see, it's basically the same, except you use an inverse cosine function instead of an inverse sine function. So let's consider the equation cosine of x is equal to 0.4, okay? And again, let's suppose that I want my answers to be in radians. And again, let's not impose any restriction on the solutions. So what do? Well, we need two base solutions, right? One of the base solutions will be given by, so the first base solution will be given by the inverse cosine of 0.4. Okay, for the same reasons as before. This is an angle whose cosine is 0.4. And that's what it means to be a solution in this equation. All right, so whatever this is, that's our first base solution. Let's compute it on the calculator. So inverse cosine function is the secondary function of cosine. So I hit second, cosine inverse. I get 1.159. Okay, so that's in radians, right? So that's like 1.159 radians. So that's my first base solution. But of course, as you know, we typically need two base solutions, right? So what's the other one? Well, you have to use your brain. So this first base solution, 1.159 radians, I don't really know exactly where it is. Let's just pretend it's like here or something. Okay, so this is 1.159 radians. Where's the other base solution? It's the other angle on the circle whose cosine is also 0.4. So where's the other angle which will have which will have the same cosine as this first one? It's the one down here, right? These two angles have the same x-coordinate, that is the same cosine. So what is that angle? There's several ways of thinking about it. Sometimes people will think of it as negative 1.159. I'm going to recommend you don't think of it that way. The reason why is a little complicated. You can, but it leads to things that are kind of annoying. It's best to think of this second base solution as, so I'll write it here, the second base solution, that is this angle here, it's best to represent it as 2 pi minus the first base solution. Do you see that this angle here is actually 2 pi minus the first base solution? Because obviously this angle here is congruent to this one, right? They're both the same magnitude. So 2 pi, obviously, is a full rotation, right? So if I take that full rotation and subtract off this angle here, I'm going to be left with this guy, right? That's how you should represent this second base solution, okay? And that'll be true anytime you're working with cosine, okay? So anytime you're working with cosine, your first base solution will be given by the inverse cosine of whatever number you have here, and then the second base solution will be 2 pi minus the first one. I don't recommend that you try to memorize this. Like, I guess you can, but you should just be able to think your way through it. Like, what am I doing? What do I need? Why is it working? And then there's no memorization needed. So anyway, we should compute this 2 pi minus that 1.159. So what is that? So 2 pi minus my previous line, 5.123. Okay, let's round that to the nearest like third decimal place. So that's like 5.124. Okay, so 5.124 radians. Cool. Okay, well, we've got our two base solutions, and now you just need to slap on a 2 pi n to each one of them, right? So x equals 1.159 plus 2 pi n. That's one formula, and then the other one is 5.124 plus 2 pi n. That's my second. And again, if in this case, there's no restriction, so there's infinitely many solutions, meaning that I have to just leave these two formulas as they are. But if I had a restriction, like zero between, like x is between 0 and 2 pi, then I would have to, start replacing n with specific values and so on. Yeah. So just in summary, just whenever you're solving a trig equation, and the right-hand side, the number that you have is not a unit circle value, right? Like, it's not like root 3 over 2 or 1/2 or root 2 over 2. If it's some random number like 0.7 or something else you don't recognize, you have to use your calculator, right? But your calculator will only give you one base solution, right? And you have to find the other one by thinking about basically the unit circle and symmetry and what we did here. And then after that, it's the same. You just slap on 2 pi n to each one of them. In the worksheet, I have you do an example where you do a tangent problem. If you're watching this, you're probably absent on this day, so maybe I'll just tell you how that works straight out. Say you had tangent x is equal to, I don't know, like 1.5 or something. How would you do this? Well, I'm sure you're not going to be surprised to find out that one base solution will be given by the inverse tangent of 1.5, right? Oops. Inverse tangent of 1.5. Okay, so 0.982, right? So 0.9827, blah, blah, blah. That's one base solution. But how do you get the other one for tangent? If you've forgotten, 0.9827, I don't know where that is. Let's say it's here or something. Angle that would have the same tangent as this angle here. The answer is it's actually directly on the opposite side of the unit circle. If you've never noticed this before, but if you ever take an angle and go directly to the opposite side of it, like say this angle versus this angle right here, like adding 180 degrees or pi in radians, those angles have the same tangent. So if this is your first base solution, then your second base solution is obtained by just adding pi to the first one. So this is your first base solution, so x could be this plus 2 pi n, and then the other base solution would be this thing plus pi. So 0.9827 plus pi, that would be your second base solution. Whatever that is, plus 2 pi n, that would be the total. These two formulas would give you the total solution set to that equation. Okay? Okie dokie.